Hello, and welcome to our presentation on the evaluation of the concrete IoT systems. I'm Pavlo Hrechko, and together with my colleague Volodymyr Lysenko, we will present an architectural analysis of two IoT product families. So for this analysis, we have selected Philips Hue as our first product, which is representing a gateway-based centralized lighting network, and Amazon Echo with Alexa as our second, representing a cloud-centric voice control system. In the next 15 minutes, we will examine the architecture of each product individually. We will map their physical and deployment views, trace their control and data flows, and evaluate how they handle critical scenarios, like secure bootstrapping, firmware updates, and system faults. Finally, we will move beyond the individual analysis to show how these two products can interact. We will show how they merge into a combined system architecture, where voice recognition data is used to drive physical actuation. Okay, so let's begin with the Philips Hue ecosystem. This ecosystem bridges the IP domain with the resource-constrained Zigbee Lightning Network, utilizing the gateway architecture to establish the interoperability between these two, on the first look, incompatible protocols. To understand how this architecture is built, let's look at the hardware. Physically, we categorize components into three groups. First, the Hue bridge, our infrastructure gateway. It translates protocols between the IP and Zigbee. Second, we have the smart lights. These are constrained, mains-powered actuators that also act as repeaters in the Zigbee mesh. And the third are user devices, like smartphones that issue command via the IP network. So now that we have defined the components, let's see how they interact in the standard scenario. So for the local control, the app sends the HTTP request to the bridge. The bridge then translates this into the ZCL message and transmits it wirelessly to the light. This local path is very optimized. It is optimized for the performance designed for a latency under 200 milliseconds. However, users often need to control their bridges when they are not on the local Wi-Fi. So therefore, for their local control, the app contacts the cloud web portals. Since the bridge sits behind the home firewall, the portal forwards the request through the persistence TCP connection that was previously established by the bridge. And once it is received, basically internal logic is very identical to the local control. Now we can visualize this connections clearly in the following diagram. So this physical view confirms this network separation. So the smart bridge, it acts as the central node connecting with Ethernet to the IP domain and via Zigbee radio to the home lightning mesh, physically bridging these two mediums. Now let's dive deeper into the look inside this bridge itself. It is mapping software to hardware, and the bridge basically is divided into two zones, communicating via the serial. So zone A is the IP, it runs the HTTP server and command processor. And zone B, Zigbee, runs the SmartLink app. Following the blue line, commands go from the processor over serial to the SmartLink, and finally go to the light's ZCL cluster. The red lines show the status data, returning from the light basically. To understand the timing of these messages, let's look into the sequence diagram. Let's analyze the turn on light sequence. The user sends the command, then the bridge sends an immediate acknowledgement even before the light turns on. This is because the protocol is stateless. The command is then serialized to the Zigbee module, which asynchronously signals the actuator. While this controlling is asynchronous, retrieving status data requires a different flow. So let's look into the monitoring. The user sends a request and gets an immediate acknowledgement. However, in this case, to get the data, the AP module must query the Zigbee module via serial. The Zigbee module then polls the light, receives the status, and passes it back to the user in the second message. Moving beyond these basic operations, let's discuss how the system basically handles new hardware. To add a device, we use the ZLL commissioning. The bridge scans and the new light responds. They perform then a key exchange to bootstrap the secure link. However, note that the ZLL standards exchange methods allow keys to be sniffed. Therefore, this creates a security vulnerability that has to be taken into the account. But once the new device is added, we have to maintain it somehow. So for updates, the SV updater connects to the web portal and downloads firmware. This binary then is transferred internally to the Zigbee module, which initiates the slow but necessary over-the-air update to the constrained lights. And finally, we must evaluate the system's reliability. So let's look into that. If the internet connection is lost, the system shows resilience. Local control remains fully operational via Wi-Fi. However, cloud services like remote access and firmware updates fail, as basically the TCP link is broken. On the second fault case, let's see when the hardware nodes themselves stop working. Then basically the device, like this node becomes unresponsive. However, thanks to the Zigbee mesh, if the failed light was a repeater, the network automatically reroutes messages through neighbors, basically through neighbor nodes, to maintain this connectivity. And lastly, we consider the impact of the user behavior. So let's say if the user sends conflicting commands. In this case, the problem is that the speed between the Ethernet and the serial might create a bottleneck. Commands are buffered and processed sequentially. And these rapid conflicts aren't discarded, but they're basically executed one after another, potentially causing the latency or stale light states. So that was it regarding the Philips Hue. Let's move on to the second product.
And next, we're going to talk about Amazon Echo and Alexa. Echo is a smart home assistant product family provided by Amazon, whereas Alexa is a cloud-based assistant which stands behind it. Our system has 5 component types, out of which 3 are handled by Echo devices. Just to begin with, the Echo device is just a small computer which runs a Fire OS operational system specifically made by Amazon, and it is responsible for protocol translation between local smart home devices and Alexa Cloud. Echo is also equipped with a speaker and microphone to listen for the user and reply to his answers. And it has some smart home control modules such as Zigbee or Matter to be able to communicate with other smart home devices and send instructions to them. The second important layer and component type is our cloud. And cloud is our main computational power. It extracts the executional logic from the user's natural language, and it is also responsible for account management and storing the data. So the core application logic runs there. Next, we're going to talk about basic use cases. For example, a user wants to retrieve some sort of information through a hands-free voice interaction. The flow is simple. The user says Alexa, namely wake word, and requests the desired information. After that, Echo records his question, applies some and noise reduction and other audio processing, which is local, and sends it to the cloud. After that, the cloud is furtherly process the audio with speech recognition and intent parsing, and generates a response on the question. After that, after the echo receives the answer in the question, it just plays it using the speakers. Another use case is if a user wants to control the connected smart home device, for example, plug thermostats or lights with his voice. So the user says the flow is simply the same until we reach the cloud. And after we reach the cloud, after the Alexa processes the audio, it establishes that the intent of the user is to execute the command, for example, set the temperature to 20. Then Alexa Cloud picks the correct command for this specific device and sends the command to the Echo device, together with the feedback about the command, like textual. For example, okay, I'll set the temperature to 20. Sometimes after that, the Echo plays the feedback and sends the instruction to the smart home device throughout this Zigbee or Matter module. However, sometimes, depending on the smart home device's protocol, or whether your Zigbee or whether your Echo device has a Zigbee module, Alexa Cloud may directly communicate throughout Cloud API, throughout the smart device's Cloud API. So there would be no instructions sent to Echo. It again depends on the protocol of the device. Next, we'll have a physical view. We have a router which connects us to the internet. We have two clouds, the smart devices cloud and the Alexa cloud, and sometimes they do communicate, again, depending on the protocol. And we have a simple access point which connects all our smart devices and Echo. And lastly, we have two users, namely A and B, which illustrate that the system can be controlled throughout the app, either locally or remotely. In the development view, the light blue boxes illustrate the Amazon's part of the system, and we also have a smart home device example as a thermostat, which has works with Alexa certificate. And since he has works with Alexa certificate, Zigbee controller is able to communicate with this device directly after the user asks for it. Yeah, and that's it for the development diagram. The sequence diagram illustrates the simple scenario where user wants to know the what's the temperature today. The flow is simple. Microphone detects the question. There is some audio processing. Afterwards, it sends it to the Alexa cloud. In the cloud, there is some further audio processing, and this all lies in the application logic layer. So, for example, speech recognition, natural language understanding engine, and skill router. And afterwards, all this is forwarded to response generator. Then the cloud generates a response that today temperature is 12 degrees, for example. The cloud sends it to the Echo, and Echo plays it on the speakers. Afterwards, the user, of course, hears the speaker's output. What do we want to add in a device which doesn't have a works with Alexa certificate? Then, as is seen on this development diagram, there is an additional box appeared in the Alexa cloud, which is marked with orange color, namely custom adapter. Sometimes this box requires manual user intervention or developer's intervention, but it depends again on the device itself. And as you can see, the link from Zigbee controller of Amazon Echo disappeared, and the Alexa cloud communicates and gains data directly from the thermostat's cloud. And we also have another app appeared in our user device. So about adding device sequence. The user needs to set up the thermostat app, configure it with a thermostat cloud, and afterwards, throughout the Alexa app, he can initiate like connection process. He needs to link an account and like basically give the credentials to the Alexa, or manage the credentials for the account linking system of Alexa Cloud, and afterwards there should be some sort of configuration of adapter so that the Alexa will know how to instruct to this new device. This is done again either by a user or by a developer, and afterwards the Alexa is fully capable of controlling this device. About the updates, so this is a deployment diagram of the update, and there are no necessary or major changes needed, as Alexa's cloud application logic is connected to Amazon Echo and Alexa app. The developers can upload and distribute the updates there if needed, and otherwise, if they want to update the Alexa cloud, they can of course access it directly and update it. For example, the sequence diagram illustrates 3 cases when the developer wants to update 3 different parts of the system, and the main difference is that how the system distributes the updates between the target of the update, and whether the user needs to confirm or initialize the update because some parts of the application may become unavailable at that moment, or Echo, for example, can be offline. What happens if internet connection is lost? All the magic intelligence is lost. There is no speech and intent recognition, and the Echo does not send the periodic keep alive calls. It also displays the red ring indicating the problem with the internet. And however, Echo may still run some small tasks, for example, alarm or turn on off instructions within the local network, so the devices still will work. What about if the device stops working? The Echo is sending periodically device status reports to Alexa Cloud, and Alexa Cloud polls the Echo's Cloud's service status. So the Echo Cloud will be informed, the Alexa Cloud will be informed if something goes wrong with it. Alexa just stops sending and routing any voice or other commands to that device, and Alexa displays this device as offline, and voice control will not work. However, the user can still play music or manipulate with that speaker. And what if the users give conflicting commands? Alexa simply preserves the last valid command wins policy, so the earliest command is cancelled, and the last command is only executed. Let's talk about the combination. So suppose the user wants to switch on or off the lights. Then the user just says it to his Echo at home. Echo sends the processed audio to Alexa. Alexa gives this the correct commands, sends it to Echo, and Echo sends them to the lights to execute the command. That's it. The other use case can be that the user wants to set a specific brightness on the smart lights depending on the current weather. Then the user needs to create a routine in Alexa app with some rules and conditions, when and what the intensity should it be. The Alexa app stores it in Alexa Cloud. Alexa Cloud monitors the weather and triggers the routines automatically. So when there is a change in the weather, Alexa Cloud sends the commands to Echo. Echo transmits it to Philips, and Philips does the command. Let's look at the development view. So we have the same view with the Amazon site. The only part is that we have a Philips lights, and that's it. And they have a communication between each other. From the sequence diagram, the flow is almost the same, and the lights will be turned on. And here are the references which were used, and thank you for viewing our presentation.